In this pre-lecture video, we're going to take a break from the concepts and we're going to start putting some math, some calculus with the things that we're learning. So we're going to put the thermodynamics to the side for the moment. I'm going to give a little bit of a review of these things called partial derivatives and differentials. Partial derivatives you've probably seen before in a calculus class. Differentials might be new, so I'll show you what that means. And then we'll talk maybe a little bit later in class about the applications of this to thermodynamics. So let's get started with that. So I hope that you know how to deal with derivatives of a function which depends on more than one variable. So for example, let's say, just as an example, is equal to bxy cubed plus c times x, with b and c are constants. And I want to take the derivative, the partial derivative, df dx, of this function. Of course, you probably already know how to do this. You treat, if I'm taking the partial derivative with respect to x, then I'm treating everything else, including y, as a constant. Even though y is a variable, for the purposes of the derivative, I keep y constant. It's equal to by cubed plus c, taking the derivative with respect to x. And then, of course, if I had the other derivative, df dy, I would treat the x as a constant. So I would have here 3bxy squared plus 0. Remember, I'm treating x as a constant, so both c and x are constants with respect to, for the purposes of this derivative. And so we are left with this expression. Okay. Now, in thermodynamics, I'm going to generally, we write it a different way. So in thermodynamics, we'll express partial derivatives this way. For example, df dx, and then I'll put an extra y here. So what this means is keep y constant. So the thing that's outside of the parentheses means keep it constant, all right? And then I could do the other one, which would be like df dy. With respect to x, that would mean keep x constant. So practically, if I want to take one of these derivatives, like the first one, take the derivative with respect to f, of f with respect to x, keeping y constant, the first thing I need to do is express f as a function of x and y, and then take the derivative. Okay, so sometimes this first step throws people for a loop in thermodynamics, because in thermodynamics we have more than two variables. You know, we have p, we have v, we have t, at least. Sometimes we have other variables as well. So there's not only two variables floating around in thermodynamics, so you have to express your function as a function of the variables that are being asked for in the derivative. Okay, so just watch out for that, and we'll do some examples of that in class. Now so that's hopefully a review. The next thing I want to talk about is these things called differentials. And it's basically the same idea, but a different way of looking at it. Maybe to illustrate it, let's focus on a function of one variable. So let's say we have x, and this will be f of x, and let's call this x1, and this will be x2 over here. And let's say the function does something like this. Okay. Suppose I want to know the change in the function f as I go from x1 to x2. So I would call this delta x. And I'll call this here delta f. That's the change in the function. Okay. All right. Let me draw here a tangent line, straight, something like this. Okay. So this is going to be the tangent line to the curve at the point x1. And that means that the slope of this is equal to the derivative f prime evaluated at x1, right? Okay, so what I'm going to try to illustrate here is what if I use that tangent line to approximate the function f? Okay, now I'm going to use the notation df to mean the change in f calculated from the tangent line. Okay. And what is df? So df on this diagram would be this height, right, from here to here. And it's going to be just df is going to be equal to the slope of the line times the change in x, right? So it's going to be the slope of the line, which is f prime of x1, times the change in x, which is delta x. Okay. Okay. Now you can see that df is not the same as delta f because the line is not exactly equal to the curve, right? So df is not equal to delta f in general. But if my delta x is very, very small, so in the limit that delta x goes to 0, so I take an infinitesimally small step in x. So I don't go very far. I go like just the smallest amount you could possibly imagine in x. Then, if I look very close here, my curve and my line are exactly on top of each other, right? So in the limit, x goes to 0, they are equal. And so therefore I can write something like this. df is equal to the slope of the tangent to the curve times dx. And, I could write this like this. The slope of the tangent, we know, is the derivative, df dx times dx, which is totally obvious if you stare at it. I mean, your instinct is, well, why can't I just cancel the dx's and I have df equals to df? So this relationship is hopefully not surprising to you. Think of, when I go forward, we're going to think of, df is a small change in small change in f. And dx is a small change in x. And then this thing is the relationship between the change in f and the change in x. That's the derivative of the function. Okay, now that is hopefully obvious, or at least makes a lot of sense. Now the trick comes when, what if I have a function of two variables? So what if I have f is a function of two variables, x and y? Now I can change f by changing either x or changing y, right? So f will change if x or y changes. And in other words, like if you've kind of visualized this, it means that, I can't just move for my x variable, I can't just move on a line forward and backward. I can move in a plane. I can move forward and backward and up and down, right? And either of those will change my value of f. I like to think about it, the analogy is kind of like, suppose f was like the height of a hill. And so you're measuring, you're standing on a hill and you're measuring your height, and x and y are your coordinates on the ground, right? So at some point, x and y, I have some height, and then I move to some other point on the hill and I have a different height. And how much the height changes will depend on, which direction I move. I could move purely in the x direction or purely in the y direction or in some angle. And all of those changes will have different changes in height. So we're going to write this kind of thing as df, that's the change in f, will be equal to the slope if I move in the x direction times dx plus the slope in the y direction times dy. Okay? And that's what the partial derivatives give you. So we write this equation here, df, small change in f, is partial f partial x, keeping y fixed, dx, plus partial f partial y, keeping x fixed, times dy. Okay. So this relationship here is really important, relating the change in the function, df, to the change in the variables it depends on, dx and dy. Now, the reason this is useful is that it's often easy to write down df is equal to something, right? We'll see that a lot of times it's going to be hard to actually calculate these partial derivatives in the normal way, but if I can write an equation like the one in the blue box there, I can read off the partial derivatives. So as an example, let's go back and do that same example that we did before, but in a different way. So I'm going to do, again, f of x and y is equal to bxy cubed plus c times x. Now I'm going to take what's called the differential. So I'm going to write df is equal to d bxy cubed plus cx. So you can think of d as being like something that measures a small change. It's kind of confusing. I'm not writing the derivative with respect to anything. I'm just looking at a small change. But this thing obeys all of the same rules as a derivative. In particular, it obeys the product rule and the quotient rule, etc., right? So let's simplify this out using those rules for derivatives. df is equal to, now the derivative is linear, so I can take the derivative of each term, d bxy cubed plus d cx. Now b is a constant, so it has no change. Right? There's no change in b, so it comes outside the derivative, just like a regular derivative. So b times d xy cubed plus c, same thing with c, d of x, like that. Okay. And d of x is just dx, right? Now, in here I've got a product, so let's do the product rule here. df is equal to b times d y cubed dx plus x times d of y cubed. And then I've got plus c dx. Okay? Almost done. The last thing I have to handle is this one. d of y cubed. What is that? Well, from what we learned above, like, y cubed is just dependent on one variable, which is y, right? So I can consider like f of y is equal to, maybe it's better to call it some other function. Let's call it g of y is equal to y cubed. And we learned before, if we had one variable, dg was dg dy, the derivative, times dy, right? So this d of y cubed is going to be equal to the derivative, which is 3y squared, times dy. So put it all together now. df is equal to b y cubed dx plus 3y squared x dy plus c times dx. Now I'm going to collect the terms proportional to x. df is equal to, let's keep the terms proportional to dx. So there's a by cubed, and then there's a plus c here. This is dx. And then from the next, the only other term left is the one proportional to y, which is 3by squared x dy. Okay. So I've written down an equation which expresses the change in f in terms of the changes in the variables it depends on, dx and dy. Okay. We're going to be using these kinds of relationships a lot in this class. Now, compare this equation with this one. Compare this equation with this one in the blue box, which is the one we already had before. So this is the particular example. That I was working out. This is for any function. F of x and y. Anytime you see an equation which looks like the one in the blue box, you can read off what the partial derivatives are. So for example, the thing in front of dx is the partial derivative of f with respect to x. So that means this is that partial derivative. And the thing in front of the dy here must be the partial derivative of f with respect to y. So that means the thing in front of the dy here must be the partial derivative of f with respect to y. So once I've written down this equation here, I already know the partial derivatives. I can just read them off. So by comparison, I can read off that df dx with respect to y is equal to by cubed plus c, and df dy with respect to x is equal to 3by squared x. Just like that. And lo and behold, this will be the same answer that we got at the very beginning. If I go all the way back, by cubed plus c and 3bxy squared here. This is what we got just by taking the derivative normally. But I'm showing you that if I do it in terms of, if I first calculate df, I can just read off the partial derivatives and I get the same answer. Right? So this agrees with what we had before. So I'm teaching you this technique of writing down an equation which looks like this and using it to read off the partial derivatives. And I know what you're thinking. You're like, well, why can't I just take the partial derivatives the way that I'm normally used to? And the reason is that a lot of times you won't know the function f of x and y, but you will be able to write down an equation like the one in the blue box. So that's why this is useful. So the application here, and this happens a lot in thermodynamics, often you won't know f of x and y, but you will be able to write down a function like the one that looks in the blue box, a differential. Df is equal to something times dx plus something times dy. So if I don't know f of x and y, I won't be able to actually calculate those derivatives the normal way. But by looking at this relationship here, I will be able to determine those partial derivatives. And that's the technique that I'm trying to get across here. All right, so just to summarize what I did is I reminded you how to take partial derivatives the usual way that you learned in calculus class. And then I talked about this thing called a differential, which is just a letter D, which obeys all the rules of derivatives. And that if you can write down a differential of some function in terms of the changes of the variables it depends on, like df in terms of dx and dy, you can read off the partial derivatives of the function f from that relationship. And this has a lot of applications in thermodynamics, and we will use it a lot. So I'm asking you to become familiar with this technique. I hope you found this useful, and we will pick it up here. We will talk about some thermodynamic applications and do some examples when we come together in class. See you all then.